Okay, so let's start now, and thanks a lot for coming, also to our speakers. This is probably the kind of nerdiest session that we have in our in our conference these days. We had actually 60 attendees registered, but what happened also for the previous session is that many people came late, and then they kept on trickling in the first half an hour. So we can start. I would like Markus Huber to make the introduction of our speakers.
Hi, good morning. Is that yes, it's on. Thanks for all showing up. Indeed, this is the most science-focused session, but at the same time, we're also gonna we're not gonna dwell on technicalities. So I'd like to introduce the panel, starting here with Gláucia Murta. She's currently a postdoctoral researcher in Delft, in the Netherlands, working on mathematical foundations connected to the quantum internet, but will soon move to Düsseldorf to a bit more senior position and is recruiting a student. Then, she completed her PhD in Gdansk in Poland. And Brazil. Ah, yes, it was just a visit. Oops, sorry. Yelena Guryanova did her PhD in the University of Bristol, UK, and then moved to Vienna as a postdoctoral researcher in quantum foundations. And she recently won one of these big Austrian research grants, this Zukunftskolleg, to start her own group together with a couple of other postdocs, and is also recruiting here in Vienna at the Institute of Quantum Optics and Quantum Information, which is also where Rupert Ursin here is located. He completed his PhD in the University of Vienna as well. Moved around as a postdoc for a long time, but is now a permanent group leader at the Institute of Quantum Optics and Quantum Information, and works on experimental realizations of quantum technologies. In particular, he's known for satellite-based communication, free space, communication of quantum particles. And myself, I'm also located at the Institute of Quantum Optics and Quantum Information in Vienna, also original graduate from the University of Vienna, and I work on theoretical quantum physics related to high-dimensional encoding of quantum information and small thermodynamic machines, or quantum thermodynamics. And with that, I'd like to pass on to Klaus Ian Yelena, who will be giving a short introduction about what is quantum. Oh, why is it such a buzz?
All right, thanks, Marcus. So the title of the session is The Quantum Frontier, From Foundations to Technologies. So in this sense, it makes sense to start from the beginning. So we'd like to start by telling the story of an interesting debate, a debate that started in the 1930s, or the late 1920s, between Albert Einstein and Niels Bohr. So this is a photo of them taken, I think, in 1927 at the Solvay Conference in Belgium. And this series of debates subsequently became known as the Einstein-Bohr debates. They're very famous now. And the crux of the debate was the following. So Einstein was very uncomfortable with the idea that uncertainty played any fundamental role in quantum mechanics, whereas Bohr thought the opposite. He thought that properties of entities, quantum particles such as electrons, are only revealed when you observe them. So until you look at something, until you observe it, you can only assign a probability to this quantum entity being in a certain state. And Bohr very much believed that uncertainty was a fundamental feature in quantum mechanics. He said that if you go to measure a quantum particle, you do so with a measuring apparatus such that you interact with the quantum particle and your apparatus in such a way that after you interact with it, some of the properties of the particle become more uncertain. So what do I mean by this? You can think of uncertainty as a disturbance. So if I want to find out the property of a particle, for instance, where it is, I have to touch it. So either with my hands, or I look at it, or I send a laser to it. And when I do this interaction, I necessarily give that object a kick in momentum. I change the velocity. Now in the quantum picture, the more I know about a particle's position, the less I know about a particle's momentum or velocity. And this was very well characterized by this famous Heisenberg uncertainty relation. Now, in these debates, what Einstein wanted to show that it was possible to perceive a part of your physical surroundings without it being disturbed by the measuring apparatus whatsoever. So in 1935, Einstein and his colleagues, Podolsky and Rosen, published this paper, Can a Quantum Mechanical Description of Physical Reality Be Considered Complete? This paper became known as the EPR paradox, because what this paper did was it outlined a thought experiment. And the thought experiment goes as follows. You have two quantum particles that share the same property. And what you do is you take these particles very, very far away from each other, for instance, to different ends of the universe, and then you measure one of them. So you ask the particle about one of these properties. Now, because you know the particles share these properties, when you measure one of them, you know instantly about the property of the other particle. Now, the point of this paper written by Einstein was to highlight that Bohr's theory contained absurdities, because how is it that you can instantly know about the property of another particle on the other side of the universe? Instantly means that you've received information faster than the speed of light. And this is in complete contradiction with Einstein's theory of special relativity. So Einstein was motivated by extending his own ideas of space-time to the atomic level. So this description of space-time he believed belonged at the atomic level. And in his view, distant parts of the universe could only be connected by signals or effects that propagate at the speed of light. And that the origins of these signals must always be traced back locally to one of the parties. So Bohr followed this up with a different paper with exactly the same title, a few months later in the same year, where he disagreed with this point of view. He argued very hard for the indivisible nature of quantum phenomena, and he said that you shouldn't be able, even though you can take these particles very far away from each other, you should still think of them as one system. So this paradox remained for many years, in fact about 30 years. So depending on whose position you took, Einstein's, whether you believe that things should have a local explanation, or Bohr's, in which case you believe that there should be a fundamental uncertainty in quantum mechanics, was a matter of taste for many years. And that is until John Bell. So John Bell was a physicist from Belfast who in the 1960s was working at CERN, at the Large Particle Collider in Geneva. And he was working as a high-energy physicist. So he published more than 80 papers in high-energy physics, so that's particle physics. But in his spare time, so at the weekends, he indulged in what he called his hobby, which was the foundations of quantum measurement. And in 1964, he published a paper that would set the foundations for quantum information and quantum computing in the rest of the field. And in this paper, what he did, which was very remarkable, which he outlined an experimental proposal for how to test Einstein or Bohr's debate. In particular, he showed that if you agree with Einstein, the results of your experiment should obey a certain mathematical relation that we call Bell inequality. If you believe in Bohr, then the results of your experiments would violate this relation. So what he did was he showed that there would be a physical test of what was causing the debate.
Yes, so I'm going to try to give a glance of what is Bell theorem is about. So that is the only technical part of the the talk. So we can this is the way I like most to see Bell's theorem. We can think about this as a game. So let's say Alice and Bob are going to play a game, a card game. So hearts and spades are reserved for their questions. So they have a deck of cards that only contains heart and spades. And they use diamonds and clubs as their answers. Okay, so they want this game. So Alice takes one card from the deck, which is her question. So she can either take a heart or a spade, and Bob do the same. And they win the game if their answers satisfy this condition. So let's say whenever they take two cards, they should always reply with the same color, so either red or black. But if they both get spades, they should reply with different colors. So these are the rules of the game. And if Alice and Bob are playing this game in the same table, they could simply, each of them take their card. They show to each other, look, I got this question. And then they could say, okay, let's see which answer we can give such that we always win this game. But now to make this game a bit more interesting, we can take Alice and Bob in separate rooms. So now they cannot know which question the other player got. So Alice doesn't know what's the question of Bob. So now how can they play this game and win this game all the time? So then we formalize that. So let's say before they start the game, they could talk and decide on a strategy. So here we are looking at the strategy 1 that Alice and Bob say, okay, no matter which question I get, I always reply with diamonds. So if they do that, here we see that if they get the first questions, they win the game. Second as well, third as well, but then the fourth, if they both get spades, they don't satisfy the condition. So they can only correctly guess 3 out of 4 of the case. So they can think, okay, but let's then do a different strategy so that we maybe can win this game always. So now Alice they said, okay, I will always reply diamonds, and then Bob, please reply with the same color as your question. So in this case, we see that now they satisfy the last condition. However, the second condition is not satisfied. So again, they only get 3 out of 4 of the questions. And I can tell you, you can think about any strategy Alice and Bob could do, the most intricate one, and you are not going to be able to come out with any strategy that can win this game with more than 75% of success. So this game sort of was the way that Bell found to capture this idea of Einstein, that if I'm looking at the response that systems that are far apart are giving, this response should have a local code. So these systems should have interacted before and agreed on a strategy on how they are going to respond. So this is, but then we see that if they are playing this game and these systems have this local explanation, I should be able to get 75%. But then, if these cards are quantum, we can actually do an experiment, and we see that actually, if they could, we could perform this game and win 85% of the time. So that means that I can't explain this success of this game with this this idea that they locally interacted and then they agreed on a strategy on how the quantum system is going to respond. So this is showing that this uncertainty of quantum mechanics is really something intrinsic that cannot be explained as a strategy previously agreed. Okay, so we saw that we can actually use quantum mechanics to win a cards game with higher probability, but then what else can we do with that? So that's maybe the origin of quantum technology. So from in the field, we have been explored and realized that we can actually use this uncertainty. And it has shown like promising results for many areas of technology, so especially communication, computing, and sensing, like to make more precise sensors. We have found algorithms that would be much more, perform much better if we would have a quantum computer, so much faster. And we also see that we can get advantage for quantum communication tasks. So now we are entering an era where we are starting to be able to manipulate these quantum effects. So here in this next picture, I'm illustrate some of the achievements that were obtained so far. So we've been able to achieve satellite-based quantum communication. So in this first picture on the top, you can see a phone call between Vienna and Beijing that was encrypted based on quantum systems. So, and also based on satellite communication. Here in this picture, the idea was to illustrate, so these 2 points are, let's say, Alice and Bob, so people were able to separate these 2 points apart for here 1 kilometer, but we are being able to achieve lately more kilometers apart, and still we can observe this quantum effect, so to preserve this quantum effect. But moreover, I would like to mention, so this is one of the experiments. So in 2016, we had 3 very important experiments in the field. So one was performed in Delft, so which is of this picture, another in Vienna, and another one in NIST in the US, where people really proved the Bell theorem. So there was experiments before, but there was still some complaints. Okay, but maybe there was some extra things that we didn't take into account, so that still quantum theory could be not so weird as we expect. But then with these experiments of 2016, then people were finally convinced. So we have this intrinsic uncertainty. On the middle top, we are illustrating some sensing device, which so we are really using quantum properties to go up to the limit of measurement precision of a device. On the top right, you can see a quantum computer, which is basically a fridge. And so we are being able to manipulate several quantum systems together, but at the moment we can only do that in very low temperatures. So. And also we are starting to have even commercially available device. So here is an example of a quantum random number generator from ID Quantique. So yeah, so we are starting to show that these phenomena are possible, and maybe soon we scale that so that it's really a technology that we can use. And then we can finally reach the point where we have all the world connected by quantum computers and being able to transmit quantum communication so that we can really explore that. So here I would just like to represent that there is several companies working on quantum technologies. So probably this is not an exhaustive list. So people are really investing in that lately. Okay, and then before we finish, I would just like to summarize that, okay, we want to achieve the future where we get all of this, where you can really explore all of the capabilities of quantum systems. And we are nowadays starting to be able to construct the devices and explore that. But the message is that all of that started with questions that were only related to the foundations of quantum theory and just curiosity-driven questions, and not immediately people could see that this would lead to technology. So that it's very important to care about foundations as well. Yeah, with that, we would like to thank you.
Okay. So thanks a lot for a nice introduction. You really very nicely simplified the concepts. One curiosity I have is if you can use it for gambling.
So
does it work?
So actually, people have made a protocol for the bridge game that you can have advantage to play bridge.
I see.
If you, yeah, but we can say more about that.
Well, only an interesting side note, one of the biggest commercial success of any quantum technological device available on the market is actually by online casinos. As sad as this is. Because they really want true random numbers, they want unpredictable random numbers, and most like other algorithms, they kind of let you predict some stuff, but so these quantum certified random numbers, they're really random. Like as they said, there's an actual uncertainty in them, and using this gives them an edge to make sure that no players can cheat. I mean, it's a bit of a lame application, but it's the commercially most successful one.
Okay, thanks a lot. Is that working? Can you hear this microphone? Okay, good. So I will start this panel discussion talking first about science and what we are learning about nature by studying this phenomena, and then passing to technology. Okay. What are, let's say, the insights that inspire you more about quantum physics? I may start with Marcus, maybe, and then you can pass it to them. So what
the insights that
yes,
inspire?
What makes you more passionate about? Yes.
So I think the most fundamental thing that I'm really passionate about is this. It's just natural science in general, where quantum physics does play an important role, but it's not the only one. It's the question of, okay, we have all of these different physical laws, models that manage to predict things that we manipulate really well, like we're doing science, but at each scale, new structures emerge. And the question is, like, how do classical structures emerge from quantum ones? How does statistical mechanics emerge? Like, there's all of these emergent laws at a new scale, but they always seem to happen at very specific scales, and they also seem to be very much connected to what kind of questions we're able to ask and what kind of things we're interested in. I mean, like the full description of a kinetic gas would, for instance, be, well, each quantum momentum and position of every bloody gas particle inside. But if we only care about the pressure and its container volts, then we can safely neglect all of these quantum effects. And basically, so the fundamental, that's why we are in like the field which is called quantum information. It's the intricate connection between information, thermodynamics, and quantum physics, or natural science in general, and how we can mathematically rigorously model the emergence of laws at different scales. I think this is one of the things I'm really passionate about.
So now I have to say something here. So I'm the only experimentalist here on the board. So these are theory guys, and they have certainly a different view. I made my diploma, my master thesis at CERN, at a very large machine there, and I did not even touch all the screws in those giant machines, and I decided to do something smaller. In a lab scale, and these quantum optics experiments, you can really touch all the screws, all the lasers, all the optics. You can really build an experiment and do something new and publish that in a high-ranking journal. This is not
with your names, right?
With the names on it, and this is not this is not for granted in all natural sciences. So this is one reason why I'm in the field. And the second reason is, as was mentioned in the beautiful talk already, that this is fundamental physics, fundamental science. We try to understand science, and at the very same time, the same machine is in my case a quantum cryptography machine. So its application and its fundamental oriented the very same machine does the same thing, and then you can always discuss things and reuse the technology for these kind of experiments or demonstrations to seed financing guys. Maybe we can talk to that later. So it's small, it's beautiful, it's simple to understand, so even I can do this. These machines are doing fundamentally interesting experiments, and it's an application. So all of this makes, this is the reason why I'm still in the field.
Okay.
I would say that I agree with Marcus mainly. I'm just interested in finding things out and the mechanism behind which things work. So it's really nice when you sit down and after maybe a few weeks of working on a problem, you feel like, I've really understood how this thing works, and for me it's nothing more than that, really.
Okay, so maybe I go more on the Rupert side, but not in terms of experiments, but also I find it very interesting that theoretically, okay, we can touch the foundations of quantum theory with very simple mathematics. And I really like to have control of the mathematics, so not of the screws, but such that, I can really know what I'm doing instead of going to the emergent phenomena of Marcus, which are also very interesting. But to me, I like to have the control, and we can really discuss all the interesting aspects with very simple mathematics, I could say.
Okay, simple for you probably, right?
No, but even in the field of mathematics, you can... It can be quite simple compared to other mathematical descriptions of systems. So that's very interesting.
Talking about simplicity, he also mentioned is simple to understand. I find that it's kind of very counterintuitive. So I think that it's a kind of hard topic, but with a simple description compared to, let's say, complex biological systems where you have many things interacting, but still it's more easier to understand from an intuitive point of view. Do you have any comments about?
I think quantum physics is the simplest. Conceptually, the basic concept of chemistry, biology, the main concepts to understand there are pretty simple. But the molecules, once you start to discuss a huge giant molecule, these things get incredibly complex. And in quantum physics, it's somehow the other way around. So once you accept, and I still believe there is only one way to understand things, which is accepting things. If you accept a few simple things, and this is only a few, I think once you accept a double slit experiment, you literally have to accept it. I mean, it's an experimental outcome, and there is no way to discuss with nature. This is a thing.
Okay.
You take it and eat it and accept it, but then it's the mathematics is beautifully simple.
You wanted to say something?
I hope you all agree with.
So there's a difference between working with the theory to understand what the equations give you and a difference in interpretation. So I would say that the interpretative side I would personally leave to philosophers, because I work with the theory directly. Okay. So I write something down, I calculate it, I look at it, and then maybe Rupert goes and tests it in the lab. How this thing actually works, it's not always described by the mathematics. The mathematics gives you a prediction or the result that you expect to see in the lab, but not always the mechanism. So sometimes people in quantum information aren't necessarily interested in really the how. This is more sort of philosophical, or the why, but they really just work with the theory sometimes.
Okay. Yeah, no, that's true. But as I said, for a double-slit experiment, right, there are consequences then on how we really perceive reality and how reality is, right? Like the way we perceive reality, we cannot understand why a particle can go through two slits at the same time, right? And so there are consequences on that. Are there any branch of physics that are going there in trying to understand how different is our perception of reality, and how since we are going to describe that reality, how the two things can go together?
So I mean, this idea of being it's very well formulated mathematically, and it's a mathematical concept that is the simple thing to understand. So in mathematics, you deal with these things called superpositions quite a lot. And it's a normal thing in mathematics. But in our ordinary everyday experience, we don't experience this thing. Yeah. But the mathematics tells us that this is the fundamental behavior on the atomic level. So, Marcus?
I see, okay.
Yeah. I might just add, and I mean, it's also wholly consistent, right? I mean, the point is, I think, we humans have a tendency of extrapolating everything to our scale. And this is why some things like relativity or quantum physics seems very counterintuitive, because things at this scale, there are effects that are washed out by emergent phenomena. And the point is, like, for instance, with the superposition, yes, I mean, it seems puzzling that a photon can go through two slits at once, whatever that should mean, because we don't see everyday objects moving in superposition, or we don't even know what that is. But there is actually a clear concept. It's about interference and certain mathematical properties. And then you ask, well, could I put a macroscopic object in superposition? And the answer is, well, yes, if you had an interferometer of the size of Earth and individual control of every electron in your body, then yes, technically you could. So the point is that somehow it seems counterintuitive, because this phenomenon doesn't occur on our scale, but and it's just our. I think that's what Rupert says with acceptance. No, I mean, you just accept. Well, okay, all our cognitive bias is towards our cognitive perception, things we're used to, things we see, and that's how we like to explain the world. That's like analogies we like to make. But the point is that they just break down, and once you accept it, yeah, well. This is what happens when you send particles through a double slit, and
I see. Okay.
Yeah, sorry.
Because I like this point of view that's more like Feynman, that there is an intrinsic difference between like quantum mechanics and general relativity, that you can frame general relativity with physical related principles. So I say the velocity of light is constant. So like maybe if you go deep on that, what is velocity, then you are going to have trouble, but you can name some principles and say, okay, the theory emerged from that. And with quantum theory, we have problems doing that. So mathematically, you can describe well, but if you say, okay, quantum theory is non-local, but it's not maximally non-local, so we do have problems to really limit only quantum theory with respect to that. So
you did well with the cards.
Yeah. But yeah, so for me, I do see that, but I agree with this, that we could just take the theory, we could accept things, and we can still enjoy the theory, but I see a difference between the two as well.
Okay.
Wait, just one more reply, sorry. I mostly agree with you. I mean, I think the point is, yeah, we can win quantumly with 85%. Why not 100%? Why not 90%? Why is it exactly 85%? But on the other hand, again, this is something like Yelena, I'd leave that to philosophers. I mean, the point is, like, we have a working theory, there's a mathematical model, I wouldn't read too much into it, it's just how we apply it, and in itself it's consistent, but yeah.
Okay, thank you. So I think that I would like to the experimental side, because it's simple, right? But I guess that it's, first of all, technically challenging. She showed that first the Alice and Bob were very, very close by, and then you have to wait a few years before they were 1 kilometer apart, right? And more than 1 kilometer apart. So, and the other thing is that even if it's a simple theory, she mentioned that many experiments had loopholes, right? And you have to think about all those things. So how challenging the two things are, the technical part and also the finding all the loopholes in the experiment.
I would start saying people are always talking about the first quantum revolution, which is the semiconductor industry. So you cannot build a classical computer without understanding a classical computer, without understanding quantum theory. And this is what we call the first revolution. And it is hard to build. We all know this is very expensive to build a CPU, and those modern CPUs get very hot when you run them. But all those, this is a quantum effect, the heat in these devices, and we know that the number of transistors in such a CPU gets smaller and smaller and smaller, so the quantum effects get more dominant. And the second quantum revolution, I think this is what we are doing. I don't like the way of explaining this in this way of thinking, but let's use it now. So we are just harnessing those effects and use these effects to do what we call a second quantum revolution. And this is how to use these quantum effects in a real application. And this is our younger generation. We are not dealing anymore so much with interpretation of quantum mechanics, but more with the application of quantum mechanics. I think it's sad, but this is maybe a different discussion. So yes, it is difficult because we have to learn a lot about technologies, high-speed electronics. We have to learn a lot from the telecommunication engineers. We have to learn a lot of technologies the telecommunication engineers gave up in the 80s because it did not work in a data transmission system in the 80s or 90s, and we are right now reusing those old technologies for our needs. So we have to learn a lot from other disciplines, mathematics. When it comes from astronomy, when you do quantum communication with satellites, believe it or not, you have to learn a lot about astronomy and also the telescopes and those kind of things. So it is challenging. It is not cheap. This is a big disadvantage in my field. It's still much cheaper than a particle accelerator, but maybe it's not true anymore when you build a satellite. But we don't do done in China, for example. So it is challenging in that sense, but the basic concepts behind that, and I insist, is quite simple.
Okay, so you have to learn a lot from different fields to build your machine, and the more conceptual part about finding and thinking of the loopholes in your experiment.
I mean, this loophole debate. The colleagues were this John Bell's theorem is quite a simple mathematical expression, and you write it down. But if you think in details how to realize all the assumptions which are intrinsically part of that theory, you easily find out that this is really not easy to build such a machine. So Alice and Bob, the two receivers of these two particles, they really it's not allowed that they have any way of communicate with each other. You just allows communication which is faster than the speed of light, because you can anyway not prove those assumptions. Then there is one way of thinking about these quantum experiments when you think the whole universe is a deterministic machine anyway. But this is a philosophical debate because this you cannot disprove such an assumption. But if you really build such a machine which really does what the theory requires, then you have to build detectors which are capable of detecting 100% of single photons at the telecom wavelength. Telecom wavelength is 1.5 microns. This is a very, very weak portion of energy. So we found some guys in NIST Boulder who built such a detector, and we illegally exported these detectors outside NATO to Austria. We actually did the experiment just a few hundred meters away from here. So this is these are military devices, and I had this literally in my pocket in across the border. So this is, you know, there are all kinds of legal problems and conceptual problems in.
Okay, that's interesting. Gláucia?
Because you are asking about the loopholes, but it was important for the proof of principle that there is this randomness. But to explore that in applications, the experiment doesn't have to be loophole free in the sense that you don't have to have space-like separation. So that meaning that the system should be very far away. I want maybe to communicate to someone that's in another room, and we don't need to explore completely loophole free for the application. So that was important for the proof of principle of quantum mechanics.
Okay, understand. Okay, thank you. I would like to switch gears now from the science to technology. Okay, so a few months ago in October, I think, there was the kickoff here in Vienna of the Quantum Flagship. So are any of you involved in this, and at which level?
I'm just, since a few days, partner in one of these giant EU projects. So this is, the flagship is a 1 billion euro investment over 10 years. We Europeans call that a large investment. In China, this is an annual investment in just one institute. This is a matter of fact, without the satellite. This is a separate investment. So this is what we call the flagship. The flagship is there to develop products. So the industry is mostly involved, and we as researchers have just a little, you know, on the steering committee side of things, our role there.
I see. So let me jump on the geopolitical thing since you've mentioned. So it looks like other countries are investing much more than Europe, China. I don't know about US, but for sure also private companies are investing a lot. I read of Alibaba, IBM, Google, the big ones. Okay, so how can Europe keep a competitive edge if they are underfunded?
Since I don't know, I pass the microphone.
Well, in the end, I'm too much of a scientist. I don't care where science is developed, as long as there is progress, it's fine. But from a geopolitical perspective, it would of course be a bit sad in some sense, no? Because I think to some extent Europe has built up one of the most, like biohistorical coincidence, one of the most extensive expertises in quantum information and quantum technologies. This is because it has been an early priority for research here, and I think it's hard to explain. I guess there are many sociological factors, right? Which topic is hot, which topic is explored, where there is investment in, and it depends a lot on specific people, their personal motivations, political constellations, and so lots of other random factors. But fact of the matter is, right now in Europe, there's one of the biggest concentrations in expertise, and well, one could just say, yeah, fine. So other countries invest and people will eventually go there. Then again, one might as well invest a bit more here and keep them here. I think, well, and okay, I'm sorry, like probably I'm the wrong person on the panel here, because I mean, I'm fundamentally anti-nationalist. No, I mean, I don't understand why we need to cling to these anachronistic concepts of competing nations. I mean, there's one humankind and so on. that doesn't mean one cannot acknowledge the reality of competing nation states that do exist, unfortunately, and also that some of these quantum technologies are, well, I would say, have potential in different directions, right? For instance, quantum crypto, it's great. I mean, you can have absolute private communication, which is provably secure, and I think privacy of information in this age is something very important. But the question is, who gets to control this technology? Is it some rather authoritarian government, some military services, or is it released via like open science to the general public? Will the devices be made available and cheap enough for people to use? I think these are pressing matters, and for that I would advocate here, because here is our sphere of influence to actually keep investing and invest more. But of course, I mean, I'm biased. I'm living off that money, so of course I will call for more investment, no?
Yeah, of course. Anybody wants to say?
So people talk about this race to build a quantum computer and for quantum technologies, but for me it's not entirely clear that when you finally build this thing, what advantage you'll have over everyone else. So it's not entirely clear what advantages a quantum computer has. So the things that I can think of are, for instance, quantum simulation. So we learn more about many body physics, things like molecules and proteins or something, ground states of energies, things like this. Okay, we can do satellite quantum key distribution to have this secure communication. But really on top of this, there aren't so many more advantages that we know of right now. So many people are working in the fields of theory to try and understand what other advantages a quantum computer or quantum technologies could bring. So it's not at all clear for the community what direction it's heading in, I think.
Oh, that's interesting. Actually, I wanted to ask, so why do we need a quantum computer?
It's a good question.
Well, okay. Again, I mean, I think a universal quantum computer, as it's often depicted, and I think in the media there's a lot of, I think it's also the researchers' fault, a lot of hype that is a bit unfounded, like as if a quantum computer would just magically enhance all our computational capabilities. One has to repeat quite firmly from a scientific point of view, this is not certain. I mean, I cannot exclude it, but the point is there is no reason to believe this at the moment. However, I still think it is a very useful endeavor, because like one of the biggest applications and one of the biggest problems in science is simulating complex systems, right? I mean, we want to do computer simulations of certain things. I mean, computer simulations drive our design of any technology that we do, from building cars, building airplanes, building lots of things. And there's one thing that is notoriously hard to simulate, and that is many-body quantum systems. Why? Because, well, a classical computer will do the simulation in a very different way than these quantum particles behave, so there's some scaling problems, and it's, I don't know, like it makes it really hard to understand small-scale complex systems, like the properties of a solid state, like what kind of, I mean, the point is, like, if you want to know, like, oh, there is this new type of metal alloy, what is its properties going to be? The best chance you have is build it and test it, because computing like each of like the solid state properties can in general, especially when the temperature goes low, be really hard. And then you can say, aha, well, what is, I mean, the best way to simulate nature is kind of nature itself, no? This is like,
I see.
And so I think in that sense, simulating complex systems, that's one edge where I think it would be very good to have one. Although, of course, we cannot really predict what we'll find. I mean, maybe all solid states turn out to be boring and we've already seen everything, but I don't think so.
Yes, I think if you're thinking about the effects that quantum technology will have on your daily life, I don't think it's going to be the case that everyone now has a quantum computer instead of a laptop that they take around with them. I think the effects will filter down through the kinds of drugs that people use in treatment of diseases, in various, I don't know, like Marcus mentioned, alloys of various materials. So things in your everyday life, but I don't think it's going to be the case necessarily that you're walking around with a quantum computer.
I see. Okay. Thank you. So I will have more questions, but I will first open the floor for questions from the people here in the room. So are there any questions? Okay, I kindly ask you to come here because we have only one microphone, so I have to pass it to you and then to them. So if you... Here you are.
Thanks. First of all, I would like to say that I was a Marie Curie fellow before. It's quantum information retrieval theory, like a project associated with it. So I also worked a little on this. And I would like to ask about how do you store this data? Like how? Because I worked with vector spaces, like in Hilbert space, or like to represent some data related to quantum information, because you need to use Hilbert space. So how do you manage storage aspects for algorithms?
Okay, so there are two things. So the outcome of any quantum experiment has to be analyzed by a classical computer. So you do all of your experiments, and then you have gigabytes of data that you still have to analyze classically. There's no way around this. Because when you ask about the properties of a particle, say spin up or down, this is a number, 0 or 1, for instance, that you log classically. So you still need a huge amount of post-processing, which is done by classical machines. In terms of storing quantum information cannot be copied. There's something called the no cloning theorem. So what is and what isn't a quantum memory is still kind of up for debate, because you cannot copy quantum information like you can do classically when you copy something like a file on your hard drive. But I think the question you're more going towards is the classical post-processing, which still has to be done on ordinary machines.
I mean, lots of people are working on quantum memories, that is, like for these quantum repeaters. No, you should be able to say more about this. But the point is, yes, sometimes, despite being non-copyable, you still would like to store the quantum state, the formal computational representation of the quantum state of a system, and that is hard. This is one of these, it's actually related to one of these pillars and one of these big European projects, possibly even the one you're in? No? Okay. And they are trying to develop quantum memories, and right now they're disappointingly short-lived, like microsecond scale memories. Okay, so I've heard some experiments with 1 second now and so on, but it's not like you can keep a quantum state stored for a couple of weeks on a quantum hard drive yet.
Okay. Any other questions? Okay, so I can ask you, so I'm curious because, you know, there are many technologies, right? We are talking about cryptography, random number generators and computers. So what are the most immediate to be on the market? Is it a quantum computer or?
So many people would now say quantum cryptography will be immediately on the market, but we will see. We don't know. It's very hard to predict the future. So we know that there is a lot of money in computation, and sorry to say, but outside Europe.
So right now there are also a lot of quantum software companies that are starting up as startups. So they're anticipating the advent of a quantum computer or something, and they're building sort of small algorithms for potential clients that may somehow, I don't know, increase the efficiency of some calculation that they do. But this is all kind of in anticipation of this.
So it's a kind of quantum simulator, or? So that you simulate to have a quantum computer and you run it on a classical computer?
Yeah, so that's what people are working on at the moment.
I see. Okay.
Yeah, maybe I would say, to me it's quite clear that it will be quantum cryptography, but but just because of this discussion of before, of the intrinsically difficult of having a quantum memory, and the fact that quantum computer still has to be on a fridge, but and for cryptography we don't need that. So
I see.
Yeah, it seems fundamentally easier. Yeah.
My point is more, who needs quantum cryptography? But this I don't know.
So probably the military. And yeah, but I've read that probably it was in some Swiss bank that they started having some communication, encrypted communication with quantum cryptography. I don't know if it was just a proof of principle, or if they followed up on that and developed the
proof of principle of the first bank transaction was done here. So from a building on this side of the university to the mayor's office at this side of the.
I see. And so the money went to the university or to the bank?
It was 1.4 kilometers. It was like 10 years ago, and what this is a scientific demonstration. So this is a fun act, more or less.
I mean, just to mention, I think there are some companies that are selling devices. I think one can argue about the usefulness. I mean, for instance, there's these companies. I think the first one was ID Quantique in Geneva. But as I said before, no, I think as far as I know, the only thing that really sells well are quantum random number generators, because some people like random numbers for simulations or for some other privacy issues to generate keys.
Yeah.
Crypto devices are also being sold. I'm just not sure to whom and to what extent. That's not my area. And there has been these kind of startups coming that sell quantum simulation devices where it's not quite clear what they're actually doing. You know, like there was this D-Wave, they sold for €1 million to some companies a big device that had many addressable quantum systems. So in some sense it was a genuine quantum device that does something non-trivial, but it wasn't even the point that they had already proven that they could get an edge or an advantage over classical computers, which has subsequently been called into question, researched, reaffirmed, then destroyed, and so on and so forth. But so like devices are on the market, it's just that I think
So you are skeptical about the true quantum nature of these devices, right? So that at some point they use some classical.
So it's not that I'm particularly skeptical. I think people are skeptical. I'm not an expert on these devices.
Okay.
I haven't looked at them, so I don't want to say something completely wrong. But one of the main criticisms is that yes, it's a quantum device in the sense that there are quantum bits. You can see coherence, you can see entanglement, you can see all of these weird quantum effects. And yes, they're interacting and they're put together. But unfortunately, for quantum computing to work in general, we don't only need some quantum systems, right? We need to be able to manipulate them in a very carefully orchestrated and specific way. And I think the debate was, are these too noisy for these carefully orchestrated dynamics to take place? Because it seems very odd in computation, but one of the fundamental difficulties is to prove how hard a problem is. I mean, and this is one of the basic things why there's still a lot of research in complexity theory, in quantum and classical complexity, because a lot of our society is based on the belief that some problems are hard without any proof. I mean, take the paradigmatic example, Shor's factoring algorithm, right? Most of our encryption in the internet and most of our privacy and bank transfers are secured by believing that factoring large numbers is a hard problem, which, and it's interesting because it's hard to check, right? If I'm given a really large number, it's very easy to check, hey, here are two factors. If you multiply them, you get this number. Multiplication is easy. Everybody can do it. Any calculator can do it. However, given this large number and not the factors, asking, well, which are the factors? Are there any? That is a really hard problem. And this kind of asymmetry of problem hardness is already a big open question in the classical realm. It's not even proven it's hard. It's just so firmly believed that our entire security depends on it. And then a quantum computer, for instance, could solve this problem almost instantaneously. It could factor any really large number if built and fault tolerantly and whatever.
I see.
And so, but also there, the question is then, is it an advantage? I mean, can we even prove that a classical computer couldn't have done the same thing? So these are the kind of questions we're still fighting with. Like, which are problems that are interesting? Which are problems that are hard? Which are problems that a quantum computer can solve? Which are problems that a classical computer can solve? And people are, of course, very particular about when we believe that this computer is really a quantum computer, and ideally, this computer would do something that provably no classical computer can. And that's I mean, that is not only technologically hard, that's also conceptually hard to prove.
Mm-hmm. That's interesting.
Just to add a note to that, so when people talk about quantum key distribution, QKD, and about the fundamental security which is proved by quantum mechanics and so on, what people sometimes fail or they neglect is that it's quantum key but classical distribution. So once you've generated this quantum key, you still have to distribute it by classical means. So this separation between the quantum part and the classical part that is unavoidable, like when you have to post-process all this classical data produced by a quantum experiment. So it's not necessarily the case that you have a quantum device and life is somehow a lot easier, because you still have to use classical devices to understand, distribute, or process the data that you're handling.
Okay, so anyways, this machine should be kind of hybrid, where part is made by a classical channel or part of the machine, right?
Exactly.
Okay, thank you. So in your presentation, you showed a kind of quantum communication network. Can you say something about it? So is it something that people are thinking about, like quantum internet? And what is it?
Okay, so I'm coming from Delft, and in the Netherlands, they are really working. They had already started working on this project that they want to connect 4 Dutch cities by quantum communication. And then what means quantum communication is that I would send some information, and information is not just a binary bit. It's not 0 or 1, but it's a quantum state. So I get this quantum state at the end, and I can do, let's say, everything with that. So I need to really transmit the quantum state. I cannot just copy or anything.
Okay.
So, I mean, everything is transmitted by light, but we should still care some other properties of that. So, so in the Netherlands, they were already working on this project. They really want to connect in the short term these 4 cities in the Netherlands, and I'm now like also working on the group that is part of a project that is funded by the European Flagship, that is the Quantum Internet Alliance. That is a big consortium between several universities, including Netherlands, France, Spain, Vienna, which then is to maybe the ultimate goal would be to scale that to make quantum connections between several cities in Europe. But in the meantime, let's say we can also just simulate what would happen, classically simulate what would happen, or study the consequences of what would happen before we get to the point of really having an experiment to do that.
And what would be, again, like for the quantum computer, what would be the advantage of having such a network?
Okay, so the first, like maybe the standard advantage would be secure communication. But this is one of the advantages that we just have a classical task that we are doing. We want to communicate classical information, and we are using quantum for that. But in our field, we have been also studying a lot, okay, what you can do that is intrinsically quantum. So you can do anonymous communication. You could maybe send a quantum information anonymously between this network. But this, I would say, it's part of the field that is starting to be explored now, since we have that maybe the imminence of these technologies. Then people are starting to be worried, okay, so what are all the protocols that we can do? And I would say we still know very little about that.
Okay. When you say imminence, can you put a date on it, or more or less? I mean, roughly 10 years, 20 years?
So the idea of the demonstration of proof of principle, for example, in the Netherlands would be in the coming 2 years. But
I see.
Then very basically such that you are just able to do QKD or manipulate 1 qubit for a millisecond. To make it really scalable, I think any date that I say, it's quite just a random number basically, because it's, yeah.
I see, okay, that's fine. And
would you put a date, the experimentalist?
So at the European Space Agency level, there are 2 running projects, and both have a goal to be on the market in 4 years. This is a public information.
Be on the market?
On the market.
Okay.
A satellite service.
Okay. So when you have satellites, for example, as you mentioned, you have huge distances, right? So I guess that one problem is to just keep the coherence of your signal or your states. How do you do that, and how difficult it is, and how much of errors there are?
So these photons, the photons, they are photons travel at 300,000 kilometers per second, so they're fast. They don't interact with the environment, which is very good on the link, very bad at the detector, because you have to build a detector which can still detect those photons. As I said, there is a telecommunication industry in space. Before I was talking about the fiber application, but now in space. This telecommunication industry ramped up like 10 years ago, and there is a company called OneWeb in the US. They provide internet access to the third world for Facebook, because Facebook are missing 5 billion users. No, right? So this is the way they see the world. And they will launch in the order of 2,000 or 3,000 satellites into space in the next couple of years. This is a Facebook project, and the backbone of that, not the connection to the villages somewhere in the Sahara zone or in India. This is still RF and cheap and low bandwidth, but the backbone of those satellites is optics. And so this is a very, very well established technology, was driven in research projects in Europe and now exploited in the US. And the quantum communication field is somehow only adapting those technologies.
I see.
So we disconnect the strong lasers of those guys, and we are connecting our quantum sources, and also on the receiver side we disconnect the receivers they use, and we use our detection schemes. So we add just a little bit of complexity to the whole system because of the timing references and those kind of things. But this is a more or less established technology. The risk to go to the market is, will there be a customers in 4 years' time? And this is nobody knows. But there are some people now who are investing a whole sheet of money in. This is a bet.
Really?
Yeah, so but you don't. When it is a private sector investment. This is not public money anymore. It's just an ESA project for quality assurance and so on. But the money comes from investments. And yes, you never know. Today there is almost no customer. I mean, we all know a few from the public media and so on, but quantum technology, quantum cryptography is not the mass market. But those satellites, if this should be a commercially viable investment, they need a lot of customers on ground.
I see. Okay, that's interesting. Since you mentioned this, right? So earlier on we had another panel where it's a big European project from climate change, and they put together researcher, students, and also investors, private sector in general, right? Is there anything like that also in the Quantum Flagship, something to boost innovation on the technical part?
Yes, but a very high abstract level, I don't understand.
I see.
So this is SAP. They have databases, and these huge databases are slow. So they talk to some quantum computer specialists. But this is not. I don't know if this is the right way of doing.
Okay, so it will be mostly kind of fundamental research thing.
It's too early to align things here, I would say.
Okay. Okay, are there any questions from? I don't know. Yeah, of course.
Yes, and I wonder about the thing you mentioned related to public keys, because there are many possible keys, you say. So how the other person finds the correct key amongst possible keys, like how the person solves the key, I would say, like the other person.
Okay, so the quantum key distribution is not based on public key, so it's a completely symmetric scheme where the...
How it is solved, I mean, like how the other person can solve it, because there are many possibilities. So she mentioned about possible keys. That's what I'm saying. Like
Yeah, I would say that ideally, so the keys that are generated, they are identical. But of course there is going to be a bit of error on that, But the quantum key, the idea of the key, it would be that it's identical. So they don't have to search for like, how can I say, compute the numbers that the product gives, the factors. But
It is identical. Why do you generate many keys? I mean, what is the logic of creating many keys if they are all identical?
oh, sorry, not identical, but the two people who want to communicate. So I want to communicate with you. So we are going to establish a key. And that is going to be established by us sharing a quantum system and making measurements on these systems. Yes. So we make a measurement, we obtain the same string of bits, which is the same for the two of us, but no one else knows about this string.
Yes, but she mentioned about possible keys. That's why I am curious about like you mentioned about key distribution. So there are different keys than I thought.
Pairwise.
It's how you distribute the quantum particles to the people. So for these particles to share the correlations, in order to produce these bit strings which are the same, these particles need to interact together. Then you need to take these particles apart and send them to the two people. And you need to do that in such a way that no one intercepts the particle. So the distribution is classical in the sense that you have to send it to the two people who are involved in the scheme.
Okay, thanks.
Okay, I have two more questions that are kind of more related to society, okay, and social impact. So there has been a recent study by the European Parliament's Research Services that says that it's important to have citizens to get involved in any process of let's say technology development, and it is important not just because of democracy or things like that, but just because then the technology acceptance is much quicker, okay, and but there is a problem with quantum physics, that it's very hard for citizens to grasp these concepts, okay? So is there anything in the Quantum Flagship or in any project you have been involved in that are aimed at kind of having citizens to understand how it works and be involved in this?
So, I mean, first, yes, there's outreach budgets and so on and so forth. But I would like to make the opposite point. I would like to say that this may be, from my point of view, almost a bit misguided. I mean, computers, like what proportion of population will actually understand the semiconductor physics behind the logical gates in a computer chip, and what is the general acceptance of computers or smartphones in the general population? I think this is not so much, I mean, this was more about usability, and I think framing science as a human endeavor in terms of immediate acceptance of technology can actually harbor some pitfalls, in the sense that you say, well, they're doing science, they're promising these amazing devices, where's my cool device, or something like this, and then it's not being delivered. And then I would really like the very point of the beautiful talk we heard is to say, well, sometimes pure I mean, one should emphasize, I think the best outreach is that knowledge for knowledge's sake and curiosity-driven research is in itself a worthwhile endeavor of humankind. I mean, and that to get people to accept investments in science, it's a bit of a dangerous path to only point at applications, because yes, true, I mean, of course, if we hadn't had quantum physics, there would be no computer, there would be no smartphone without, well, a combination of lots of sciences, and without advances in medicine, we'd still be dying of now curable diseases and so on and so forth. This is great to understand, but it's also important to emphasize the time lag between these things. And I think also, like, in the end, I don't know, like, I think quantum communication or quantum physics and the distribution of quantum states is a super interesting and worthwhile endeavor. Whether a general market accepts this technology or not, I mean, it may just be that turns out in 100 years' time nobody is interested in information security or privacy of information. I mean, this is super abstract, right? Because now we also think, yeah, our information is kind of private, but maybe not. You know, nobody really understands encryption and how it works and how private it really is. So I think the only thing that could drive more interest in quantum crypto commercially or acceptance in society is some more NSA scandals or something like this, when people start getting worried, oops, am I being listened to or something?
I see.
I don't know.
Okay, thank you. So the other question is kind of related to that. I've recently read from a think tank in Barcelona that they had a paper about quantum terrorism. So, is there anything?
Oh my God.
Is there kind of any potential dark side of this technology, let's say, that are already kind of expected, or people are not talking about that?
What is a quantum terrorist?
I don't know.
Okay.
Not about quantum terrorism, I don't know, but so maybe, yeah, that's something that we should think about, like making policies at the same time that we develop the technology. But I would say at the moment we know like how we look at quantum technology and how it would affect the classical technologies that we have. This is mostly what we have been so far, but then there will be new things afterwards that maybe they have no completely no analog with what we have now. So then we would have to think about the policies over how to use this technology. But yeah.
Okay.
I mean, maybe in general, I think it's about social equality again. I mean, the point is, I think that luckily, like, I think quantum technology cannot be weaponized as such. We deal with very small quanta of light or things like this, and then so this is not. It's luckily not one of these high energy endeavors, but I think information security again, or the capability of doing very powerful simulations for, say, drug development or materials design. There, I think the biggest danger is that this is not distributed equally among the world and among the citizens of a country, right? I mean, if only secret services, governments, or big corporations are able to communicate securely, if only certain private entities manage to patent and produce certain, I don't know, say maybe even life-saving drugs, this can be a problem for society, and especially if all of the research that is funded, it has come from tax money in the first place. So I think one of the biggest threats coming from all of this quantum technology development is that we need to take care that it is really available openly to those that have actually funded this research. Even if they hadn't, I would still advocate this, but in light of this, it's very easy to argue.
Okay. So are there one question here?
Thank you very much. My name is Afrodita. I come from Kosovo, and I'm a project manager by profession. First of all, I want to compliment you for choosing this area, because for us, when somebody speaks, try to make an issue complex, we say, "Oh, don't pretend it's not quantum physics." So it's, it's great that you actually chose this area and make sense out of it for us. And I have just a small question, maybe. Currently, we are, as general population, is being aware of the risks of us sharing our own information voluntarily, first of all, or involuntarily. What is your view in the future? Like, will we, as general population, be more aware of what we're doing with sharing something? I mean, where do you see this going? So, like, we are now more aware, or maybe I shouldn't post this on Facebook, or from the latest developments. So how do you see this going? Will people be more, like, careful, or,
Do you have any comments on that?
Yeah, so or my point of view, I see people becoming more aware of that, because maybe like we were not even aware of like where we were sharing things, and now we are starting to see, oh, okay, it's everywhere, everyone can see it. Not that quantum mechanics would make any difference for that. I don't see any difference on that respect, but yeah, I think we are learning from mistakes that we are seeing, like what are the consequences of not being of sharing our information everywhere. But that's how I see it. But
okay. So if there are not any more questions, I think that we can close the session now, and thank our speaker for being here and giving us these insights about quantum frontiers. Thanks a lot.